Hello everyone, welcome to this lecture. In these last few lectures, we are going to focus our attention on applications of experimental model analysis and some other tasks where the experimental model analysis output can be used. One primary application of experimental model analysis is in avoidance of resonant operation of machines and structures and in troubleshooting vibration and noise problems. Now, from experimental analysis, we get a model of the structure, which is a mathematical model of the structure. And there are many other ways in which this mathematical model can be used. So, two of the applications where this model can be used are response simulation and force identification. So, in this lecture we are going to study response simulation and force identification. So, before we talk about these applications, let us try to understand that why it is said that the experimental model which is obtained is an incomplete model. So, compared to an FE model, the model obtained from EMA is not generally complete. So, if you look at the FE model, the degree of FE model could be M, capital N, and the model obtained from EMA when compared to this degree of freedom is generally incomplete, and it is incomplete because of two reasons. One is referred as coordinate incompleteness and other is referred as model incompleteness. So, what is coordinate incompleteness? Coordinate incompleteness refers to lack of measurements of many degrees of freedom which are there in the FE model, but which are unmeasured in the experimental model. FE model has large number of degrees of freedom. So, it is impracticable to take measurements at all these degrees of freedom. The other reasons are that some of these degrees of freedom cannot be measured robustly. There are no robust transducers available for taking these measurements. For example, in 1D and 2D kinds of structure like beams and plate structures, the degrees of freedom which are relevant are the translational degrees of freedom and rotational degrees of freedom, which are basically the slopes at different points, right. So, while the translational degrees of freedom can be reliably measured, however, the measurement of vibration along rotational degrees of freedom cannot be done so robustly because there are no very reliable transducers available. So, therefore, rotational degrees of freedom generally are unmeasured in the experimental model. Also, in structures which are of 3D nature, like which are in solid in nature, so they also have degrees of freedom inside the volume of the solid. And then the measurements obviously cannot be taken at those points which are inside the body or volume of the solid. So, those degrees of freedom, although they are present in the FE model, no longer can be measured. So, therefore, we see that the number of degrees of freedom which are there in the model in the mode shapes which are identified from experiment, the number of degrees of freedom there are far less than the degrees of freedom of the FE model, and that is why in terms of coordinate which are measured, the model is incomplete. The other incompleteness is associated with the number of modes that are measured, and that is referred as model incompleteness. So, the number of modes which are measured in the experimental model analysis, they are far less than the number of modes which are there in the FE model. So, if the FE model has degree of freedom n, then there are n number of modes the model can predict. But in the experiment, generally we will have a limited frequency range over which the measurements would be done. So, this is constrained by limits on the frequency range of excitation, limits on the frequency range of transducers, and the limits on the measuring instrumentation that is used, and therefore, the number of modes which are there in the experimental model they are limited. Therefore, the model which is obtained through EMA is incomplete from this perspective as well, right. So, if you look at, let us say, the eigenvalues and eigenvectors, right, which we get from the experimental model, then we will have, say, m number of modes that are measured. So, there will be m number of eigenvalues and m number of mode shapes, right, and let us say the measurements have been taken at small n number of test points. So, the number of elements in the mode shapes would be equal to m. So, this makes the eigenvector matrix to be of order small n by m, and the eigenvalue matrix will be of order m by m. It is a diagonal matrix and there are m number of eigenvalues on the diagonal. So, when these matrices are compared with the degrees of freedom of the FE model, we see that their order, number of rows and columns in these matrices is far less than the degree of freedom n, capital N, of the FE model. Therefore, the model we obtain is incomplete when compared with the corresponding FE model. So, let us now try to see that is it possible to identify spatial model of the structure from the model. So, can we identify the spatial model of the structure from the model? So, there is theoretical relationship between the model characteristics, that is eigenvalues and eigenvectors, and spatial matrices like stiffness matrix, mass matrix. So, theoretically there are relationships between modal characteristics and the spatial matrices, mass matrix, stiffness matrix which make up the spatial model, and eigenvector matrix and eigenvalue matrix which make up the modal model. So, we have the relationships between them, right, in the form of the orthogonality relationships. So, what are orthogonality relationships? So, we have seen earlier that the orthogonality relationship with respect to the mass matrix is given by phi transpose m phi is equal to unity matrix. So, here phi is the matrix of mass normalized eigenvectors, right. Similarly, with the stiffness matrix we have this relationship, that is phi transpose k phi is equal to diagonal matrix of eigenvalues lambda r. Now, from these relationships we can easily obtain m and k using these expressions, right. So, m is equal to phi transpose inverse into phi inverse, and k would be equal to phi transpose inverse into eigenvalue matrix and phi inverse. So, here we see that to obtain mass and stiffness matrix we need to invert the eigenvector matrix. We have the inverse of eigenvector matrix which is appearing here, right, in both these expressions. Now, the eigenvector matrix can be inverted if it is a square matrix, and we just saw that eigenvector matrix obtained from the experimental model analysis is incomplete. So, it is of order small n by capital M, right, where small n is the number of degrees of freedom where the measurements have been taken, and small m is the number of modes that have been identified in EMA, right. So, therefore, the eigenvector matrix is rectangular matrix, and therefore, the inverse cannot be taken, right. So, that is one reason for which cannot use these relationships to identify mass matrix and stiffness matrix. Also, if somehow we ensure that the number of test points n is equal to number of modes that are being identified, then we will have n is equal to m. It is therefore possible to conduct the model test ensuring n is equal to m. Therefore, the eigenvector matrix becomes square and the inverse can be taken. However, though we can use these relationships to find an estimate of m and k, but these estimates will not be very accurate estimates, because the number of modes m will be far less, and therefore, the estimates of m and k will not present the structure very well, right. So, therefore, because of these reasons the estimation of a spatial model of a practical system from the model identified from a model test is not feasible. Let us now look at the task of response simulation and how experimental model analysis helps in performing the response simulation. So, response simulation basically refers to simulation of response of a system to given set of dynamic forces. So, in the design cycle of a product there is a relevant question that can the proposed design sustain the dynamic loads expected in service. So, we would like to know whether the product when it is built based on the proposed design, can it sustain the dynamic loads which it is supposed to experience in practice. We would like to test that. So, one approach in ascertaining this could be to build a prototype of the product based on the proposed design and then perform the dynamic test on it, right, which means subject the product to the dynamic loads, right, means test its operation and check whether it can sustain the dynamic loads or not. If the test fails, then we will have to revise the design, make a new prototype and again subject it to the dynamic test and check whether it can sustain the dynamic loads or not. So, it will be a series of tests which might have to be conducted in order to assess the design. So, this approach is quite uneconomical and takes lot of time. So, there is always an emphasis and objective to reduce the extent of physical test in the design cycle. So, in this context the experimental model identified from EMA can be used for response simulation. So, we need to have one prototype of the product based on the proposed design, so that the model test can be conducted and then the model can be identified, and then this model can be used for predicting the response of this product to any forces which are likely to be experienced by this product in its service. Also, we will later see that if there are some design modifications, small design modifications we want to make, then the effect of those modifications on the dynamic characteristics can also be evaluated using the experimental model. That application we will study later. So, how to perform response simulation? So, what we do is that once we get the experimental model from the model test, then we can compute the receptance FRF matrix of the system, right, and we have studied earlier the relationship between the receptance FRF matrix and the model. For a multi-degree of freedom system with non-proportional damping, this relationship is given by this expression. So, this relationship we have studied earlier. So, here you can see the phi is the experimentally identified eigenvector matrix. So, there are n number of degrees of freedom at which measurements were taken, and there are m number of modes that were identified. And when the non-proportional viscous damping model is identified in the model test through curve fitting, then we get m number of complex conjugate mode pairs. So, there are 2m number of total modes which consist of m number of complex conjugate mode pairs. Okay. So, therefore, using these eigenvalues and eigenvectors, we can obtain the receptance matrix. So, there are n number of degrees of freedom where the measurements were taken, and there are n number of elements in the mode shape. So, now we can find FRF between any two combination of these degrees of freedom. So, that effectively gives us receptance matrix of order n by n. So, this n by n matrix now can be used for determining the response of any forces that might act on the system. So, if the forces are harmonic, they are of some frequency omega, right, and let us say they are represented by vector f, then the response x can be obtained by this relationship. We already studied this relationship between the response x, the receptance matrix alpha, and the force vector f. So, then we can predict the response x to any set of forces at frequency omega acting at any of these n DOFs. Now, if the forces which are acting, they are not harmonic, okay, they are, let us say, transient forces acting or periodic forces acting, then we can use Fourier series technique to present these forces as a sum of harmonic forces, okay, and then we can find response to all those harmonic components, and then using the superposition principle we can algebraically add all those responses in order to find a response of the structure, right, to the transient and the non-periodic forces. So, therefore, for non-harmonic forces we can use Fourier series expansion and superposition principle to find a response, and this, of course, superposition principle is based on the assumption that the structure is linear, right. So, in this way we can simulate the response of the system. The other application where the experimental model can be used is force identification. And what is force identification? It refers to identification of dynamic forces a system or a structure is subjected to during its operation. So, here the task is different. Here we want to know that what are the dynamic forces acting on the system, and the process of identification of these forces is referred as force identification. So, of course, one question arises that why knowledge of these forces is required, is it useful? So, of course, this knowledge is useful because if we know the forces which are acting on the system accurately, then we can design the system better, right. So, therefore, it is necessary for design. So, one approach to know these forces is to directly measure these forces. So, we can directly measure these forces by mounting force transducers. It is, however, seen that the direct measurement of the operational forces by force transducers is difficult due to the transducer mounting issues and associated necessary modifications which need to be made into the system. So, if we want to measure the forces directly, then the force transducers, load cells, these need to be mounted. For example, if a force transducer is to be used, then it should be mounted such that the force which is to be measured passes through the force transducer, right. It has to be in the path of the force transmission. So, then therefore, some arrangements need to be made. There are some modifications which may have to be made in order to install or mount the force transducer in the appropriate path. So, these are the practical difficulties which are there in the direct measurement of these dynamic forces. So, if there is a procedure which can bypass these difficulties, then that would be preferable. And then experimental model now can be used for indirect identification of these dynamic forces. So, it does not depend on direct measurement, but it performs indirect identification from the measured responses and measured frequency response functions. So, these forces can be identified indirectly from the measurement of the system response to the dynamic forces and FRFs. So, instead of measuring the dynamic forces, what we measure is the response. So, measurement of response is much easier as compared to direct measurement of the forces. So, we measure the response of the structure to the dynamic forces at several points. We also measure the FRFs, and if we have a model, then we can also identify FRFs from the model and then use those FRFs and the measured responses to identify the dynamic forces. So, there are two methods. Let us look at those two methods, how force identification can be done. Also, the point to be noted is that the force identification is an inverse problem, right, because here we are trying to identify the inputs which are acting on the system from the knowledge of the outputs and the system properties. So, from the output and the system properties we are trying to estimate or identify the inputs, and hence it is a inverse problem. The response simulation was a direct problem, where we are trying to determine the outputs from the for the given inputs and the system properties. So, inverse problems are more difficult than the direct problem. Inverse problems involve estimation of some unknown quantities, and therefore, that may face numerical difficulties, ill conditioning issues. So, let us look at the FRF best method, right, for force identification. So, this FRF best method is based on this relationship between the outputs and inputs in the frequency domain. So, let us say the forces might act at q degrees of freedom, right. So, those are the possible locations where the force might act on the structure, right. So, and let us say we take measurements of response at n number of points, small n number of points. So, the relationship between the response at n points and the forces which might act on the q degrees of freedom is given by this relationship, right. So, x is a vector of size n by 1, the force vector is of size q by 1, and these responses and forces, they are related by the receptance matrix alpha, which will be of size n by q, right. So, it contains the frequency response function at any 1 degrees of freedom corresponding to the response coordinates, and any 1 degree of freedom from the force coordinates. So, there are n into q number of FRFs. So, this matrix equation essentially represents n number of linear equations in q number of unknowns. What are unknowns? The forces at q locations are unknowns. We need to solve these linear equations to find forces. To solve this linear equation in some unique way, we ensure that the number of measurements n is more than the number of forces that are to be determined, that is q. So, this way the equation will be an overdetermined set of linear equation, and then we use a least square solution to solve these equations, right. So, the least square solution of this equation is given by this equation. So, f of omega is equal to inverse of the product of the Hermitian transpose of alpha multiplied by alpha, and this is multiplied to the Hermitian transpose of alpha, right. So, because alpha in general is a complex matrix, right, and that is why Hermitian transpose is taken here. This equation gives us the estimate of f. So, therefore, to implement this method we need to measure the receptance matrix of order n by q, and also take measurements at n number of degrees of freedom. Now, this expression needs to be evaluated at each frequency omega, because this equation is applicable for a particular harmonic frequency omega. So, if the force is, let us say, transient force or a non-periodic force, then there will be number of frequency components over a frequency range. So, we need to implement or evaluate this expression at each of the frequency lines in the frequency range, right. So, that will yield a frequency domain representation of the forces that are acting on the structure. So, at the end of identification we will have estimate of the forces in the frequency domain, and if we want to have a time domain estimate, then we can take inverse FFT of that frequency domain estimate, right. So, this estimation process may also face problem due to ill conditioning of the system of equations which are to be solved, and the ill conditioning may occur because of the ill conditioning of alpha, right, and this alpha may become ill conditioned at resonant frequencies. So, when the omega matches or coincides with any of the resonant frequencies omega m, then the FRF will be dominated by that particular mode. So, the contribution of that particular mode will dominate all the FRFs in the FRF matrix, which has the consequence that the rows and columns of FRF may become dependent, and the rank of the FRF matrix will not be full, and that will pose difficulties in the computation of inverse in the for finding the least square solution. So, because of that, what happens, the determining the forces at those frequencies will be inaccurate. So, this is one of the issues in the use of this particular method. So, approaches based on regularization techniques have been used and suggested in order to overcome this ill conditioning and obtain a more reasonable estimate of the forces at those frequencies. So, there is another method of force identification, and that is called modal coordinate transformation method, right. So, it makes use of the modal model which is obtained from the measured FRFs. So, this consists of 3 steps. So, the first step involves the estimation of the modal responses from the physical responses. So, let us say we have the experimental model available to us, identified using experimental model analysis, and this model consists of eigenvector matrix and eigenvalue matrix. And let us say the eigenvector matrix is of order n by m, which means it has n number of mode shape elements and there are m number of modes in it. So, what we do now, we take measurements at small n number of points on the structure, and those measurements are represented in the frequency domain by x of omega, right, vector x of omega. And then now we estimate the modal responses from the physical responses, because we know the relationship of modal transformation between the physical responses and modal responses. So, if you recall, that relationship was x is equal to phi into y, right. So, these are again a set of linear equations. So, if I know x, how to find y, that is the problem of identifying modal responses from these equations. So, therefore, by taking pseudo inverse of the mode shape matrix, we get this expression, right, which is vector y is equal to pseudo inverse of phi and multiplied by the vector of responses x. So, in order to have an accurate estimate of modal responses, the small m should be more than the number of modes m, or the number of modal responses. So, once the modal responses are available, the next step is to find the modal forces from the modal responses. And for the case of, let us say, multi-degree of freedom system with proportional damping, we earlier derived this relationship between the modal response y and the modal forces Fr, right. And therefore, if we take inverse of the coefficient matrix there, we get this expression which is shown here, right. So, this is the vector of modal forces is equal to a diagonal matrix multiplied by the vector of modal responses. And because the model is available, we know the natural frequencies, that is all the values of omega r on the diagonal. We also know the modal viscous damping factor zeta r. Therefore, here there is no estimation involved, we basically are computing the modal forces from the modal responses. The next step then is to estimate the unknown physical forces from the estimated modal forces. So, vector of modal forces is equal to phi transpose vector of physical forces. So, if you take pseudo inverse of phi transpose, we get this relationship, that the physical forces, that is vector capital F is equal to pseudo inverse of phi multiplied by vector of modal forces. So, here again, in order to have an accurate estimate of the physical forces from the modal forces, the number of modes m should be more than the number of forces q that need to be determined. So, then the estimate would be accurate. So, these 3 steps can be now implemented at each frequency omega, right, in order to find the physical forces corresponding to each frequency in the frequency domain. So, one advantage of this method is that the pseudo inverse needs to be computed only once. The pseudo inverse of the mode shape matrix phi, it can be computed in advance, and then these 3 steps can be implemented at each frequency. So, the pseudo inverse remains same at all the frequencies, and hence its computation need not be repeated at all the frequencies. So, these are the 2 methods of force identification, the FRF-based method and modal coordinate transformation method. So, in this way we come to the end of this lecture. So, today we looked at initially what is an incomplete model, why a model obtained from EMA cannot generally be used to identify spatial model of the system, and then we looked at the 2 applications of EMA, that is response simulation and force identification. Thank you.